Today we will look at some problems about the rainfall excess and the time of concentration. For the first problem, we need to determine the SCS runoff depths from a watershed located in Miami, Florida for a 10-year, 24-hour storm. And the watershed contains 25 acres of commercial development and 75 acres of townhouse. And the soils in the region are sand and gravel. We also need to determine the volume of runoff for the watershed in acre feet. So, based on the second paragraph, on page 413 in the textbook, and we know that the sand and gravel belongs to the hydrological soil group A soil. So based on table 11.7 in the textbook, for commercial development, we can find that the CN1 should be equal to 89, and for townhouse development, CN2 should be equal to 77. Then we will use area as a weight to calculate the practical CN. So the practical CN should be equal to the A1 times CN1 plus A2 times CN2 divided by the A1 plus A2. And from the problem, we know A1, the area of commercial development, equals 25 acres, and A2, the area of townhouse, equals 75 acres. And we know CN1 equals 89 and CN2 equals 77, so we can determine the practical CN should be equal to the 80. And from equation 11.6, for the British unit system, the S should be equal to 1000 minus 10 times Cm divided by Cn, and we know the Cn equals 80, so we can determine the S should be equal to the 2.5 inches. And from this figure 11.5 in the textbook, the Miami is located in here, and we can determine that the 10-year 24-hour rainfall should be equal to 9 inches. And from equation 11.5 in the textbook, we know the runoff depths R should be equal to the P minus 0.2 times S to the power of 2 divided by the P plus 0.8 times S. And we know the S equals 2.5 inches. And we know the the total rainfall depth equals 9 inches. So we can determine the runoff depth R should be equal to 6.57 inches. So the runoff value volume should be equal to the depth times the area, so equals 6.57 over 12 feet times 100 acre. So the runoff volume equals 54.8 acre feet. So we finished this problem. For the second problem, a 100-hectare watershed is composed of 3 different land uses: 20 hectares of golf course, 40% in Drexel soil, and the rest in Bremer soils, 30 hectares of commercial area in Bremer soils, and 50 hectares of residential area, 1/2 acre lots and Dolic soils. So we need to determine the runoff volume from a 15 centimeter storm. So based on the soil descriptions and the second paragraph, on page 413 in the textbook, we can determine that the Drexel soil belongs to the group B soils, and Bremer soil belongs to the group C soils, and Donic soil belongs to the type A soils. So based on the table 11.7 in the textbook, we can determine that the CN1 equals 16.1. This is for the 40% of golf course, and we assume it is good condition, open space, and the group B soils, and CN2 equals 74. This is for the rest of the golf course, so it is 16% of golf course, good condition, open space, and it's type C soil. And CN3 equals 94. This is for commercial area, type C soils, and CN4 equals 54. This is for residential, 1/2 acre lots, type A soils. So then we will use area as a weight to calculate the practical CN value. So CN, the practical CN value should be equal to A1 times CN1 plus A2 times CN2 plus A3 times CN3 plus A4 times Cn4 divided by the A1 plus A2 plus A3 plus A4. And we know the A1 should be equal to the 40% of the golf course. So equals 40% times 20. So A1 is 8 hack. And A2 equals 16% times 20. So it is 12 hack. And we know the A3 is 30 hack. And A4 is 50 hack. And we also know Cn1 equals 61, Cn2 equals 24, Cn3 equals 94, and Cn4 equals 54. So we can determine the practical Cn value should be equal to 69. And from equation 11.7 in the textbook, for the SI unit system, we know that S should be equal to 25,400 minus 254 times Cn divided by the Cn. And we know Cn equals 69, so we can determine the S is 114 millimeter. And from equation 11.5 in the textbook, we know the run of depths R be equal to P, the total rainfall depth, minus 0.2 times S to a power of 2 divided by the P plus 0.8 times S. And from the problem, we know the P is 15 centimeter. So the P equals 150 millimeter. And we know the S is 114 millimeter. So we can determine the run of depths should be equal to 7.1 millimeter. And so the run of volume equals 0.0671 meter times 100 hack times 10,000 square meter per hack. So the raw volume equals 67,100 cubic meters. So we finished this problem. For the third problem, we need to determine the type of concentration for the runoff from a concrete parking lot. The overland flow segment is 25 meters long with a slope of 0.5%. The overland flow segment moves water into a shallow V channel, dropping 2 meters in elevation over 100 meters in depth. Finally, the stormwater is picked up in a 400 meter long, 2 meter wide rectangular channel flowing 0.5 meter deep. The concrete channel has a slope of 1%. We need to determine the time of concentration in minutes and we know the 2-year 24-hour rainfall depth is 4 centimeter. We also need to determine what percent of the time of concentration is attributed to the 25 meter of overland flow. So let's start with sheet flow. The overland flow is sheet flow. And since the unit in this problem is a SI unit system, so we will use equation 11.12 in the textbook to determine the TT1. So we know the TT1 equals 0.091 times n times L to the power of 0.8 divided by the P2 to the power of 0.5 times S to the power of 0.4. And based on the table 11.9, we can find that the N for the concrete parking lot, the N should be equal to the 0.011, and we know the length L equals 25 meters, and the P2, we know the 2-year 24-hour rainfall depth is 4 centimeters, so P2 equals 40 millimeter, and the S equals 0.005. So we can determine that the TT1 equals 0.043 hours. And for the shallow concentrated flow, and from equation 11.14, we know the V should be equal to the 6.19 times S to the power of 0.5. And from the problem, we know the S should be equal to the dropping 2 meter in elevation over 100 meters in S. So the S should be equal to 2 meters divided by the 100 meters. So S should be equal to the 0.02. So we can determine that velocity equals 0.88 meters per second. And we know the TT2 equals L over the V, so equals 100 meter divided by 0.88 meters per second times 1 hour divided by 3600 second. So we know that TT2 equals 0.032 hours. And for the open channel flow, we need to determine the hydraulic radius first, and we know the RH equals A over P. And from this problem, we know the A should be equal to 0.5 meters times 2 meters, so equals 1 square meter. This is water depth, and this is the bottom width. And the P, which is the perimeter, equals 2 meters plus 2 times 0.5 meters. So the P should be equal to the 3 meters. And so we can determine that RH should be equal to 0.333 meters. And based on the Manning's equation, we know the V should be equal to the 1 over N times RH to the power of 2 over 3 times S to the power of 1 over 2. And based on the table 11.10 in the textbook, we can find that for the concrete channel, the N should be equal to 0.013, and we determine that IH is 0.333 meters, and the SE, the S, equals 0.01, so we can determine the velocity equals 3.69 meters per second. So TT3 should be equal to the L over the V equals 400 meters divided by the 3.69 meter per second times 1 hour divided by the 3600 seconds. So we can determine that the TT3 equals 0.03 hours. So now we know the time of the concentration Tc should be equal to 0.043 plus 0.032 plus 0.03. So this value is 0.105 hours. So also equals 6.3 minutes. And we also need to determine what percent of the time of the concentration is attributed to the 25 meters of over nanoflow. So the percent due to over nanoflow should be equal to the 0.043 hours divided by the total hours is 0.105 hours. So this value is 14.1%. We finished this problem. For the fifth problem, the hydraulic length for watershed is 2,800 feet. Along this path, runoff initially travels over the net surface, and we know dropping 3 feet in elevation over 150 feet in length through a short grass, and then moves into shallow concentrated flow for a distance of 450 feet with an average velocity of 2 feet per second. And the remainder of the travel path is through a 2 feet diameter pipe flowing half full on a slope of 1%. We need to determine the time of concentration in minutes, and we know the 2-year 24-hour rainfall depth is 3.4 inches. We also need to determine what percent of the time of concentration is attributed to the 150 feet of over net flow. So the method to solve this problem is very similar to the previous one that starts with the sheet flow 2. And things unit in this problem is British unit system, so we will use equation 11.8 in the textbook to determine the TD1. So we know the TD1 equals 0.007 times n times L to the power of 0.8 divided by the P2 to the power of 0.5 times S to the power of 0.4. And based on the table, 11.9 in the textbook, and we know the answer is short grass. So we can determine that the n should be equal to the 0.15, and we know the length L equals 150 feet, and the P2 equals 3.4 inches, and the S should be equal to the 3 feet divided by the 150 feet. Since we know the dropping 3 feet elevation over the 150 feet in the length, so the slope should be equal to the 0.02. So now we can determine that the TT1 should be equal to the 0.219 hours. So for the shallow concentrated flow, we know the average velocity is 2 feet per second, and we know the TT2 should be equal to the L divided by the V. So we know the L equals 450 feet divided by the 2 feet per second times 1 hour divided by the 13600 second. So we can determine that the TT2 should be equal to 0.063 hours. And for the open channel flow, we need to determine the hydraulic radius first. So we know the RH should be equal to the A over P. And since we know the runoff is through a 2 feet diameter pipe flowing half full, so we can, the A over P should be equal to the pi times D over 2 to the power of 2 times 0.5 divided by the pi times D over 2. So this value is D over 4. And we know the D, the diameter of the pipe equals 2 feet. So we can determine that the RH should be equal to the 0.5 feet. And based on the Manning's equation for the British unit, the V should be equal to the 1.49 over N times RH to the power of 2 over 3 times S to the power of 1 over 2. And based on the table 11.10 in the textbook, and for the concrete pipe, N should be equal to 0.013. And we know the RH we determined is 0.5 feet, and the S is 1%. It's 0.01. So we can determine that the V should be equal to the 7.22 feet per second. And we also know the TT3 should be equal to the L over the V, and the length of the open channel flow should be equal to the total length of the flow path minus the flow length in the sheet flow minus the flow length in the shallow concentrated flow. So L should be equal to the 2800 feet minus 150 feet minus 450 feet. So the L should be equal to 2200 feet. And we know the V equals 7.22 feet per second. So we can determine that the TT3 should be equal to 2200 feet divided by 7.22 feet per second times the 1 hour divided by the 3600 seconds. So we can determine that T3 should be equal to 0.085 hours. So now we can determine the time of the concentration Tc should be equal to 0.219 plus 0.063 plus 0.085. So the value is 0.367 hours. This value also equals to 22 minutes. And now we can determine that the percent due to overland flow should be equal to the 0.219 hours divided by the total hours, 0.367 hours. So the value is 16%. So we finished this problem. For the fifth problem, a comment is made in paragraph which follows equation 7.14, suggesting the selection of the radius of influence R0 can be somewhat arbitrary. And suppose the radius of influence for 20 centimeter diameter well is approximately 250 meters plus or minus 50 meters. And we need to determine the percent error in discharge that results from this plus or minus 20% change in the radius of influence, and assume a 50 meters thick unconfined aquifer with a drawdown at a well of 3 meters. So for this problem, first we need to obtain the K value. So from the table 7.2 in the textbook, and we know the unconfined aquifer is a coarse sand. Oh, I think this should be coarse. So coarse sand. So we can determine that the K value is approximately equal to the 1 times 10 to the power of -3 meter per second. And then we need to determine the discharge at a different radius. So apply equation 7.14 in the textbook, and we know the Q should be equal to pi times K times H0 square minus HW to the power of 2 divided by the natural log of R0 divided by the RW. And we know the K should be equal to 1 times 10 to the power of -3 meter per second. And we know from problem H0 should be equal to 50 meters. And we know our drawdown S equals 3 meters. So we can determine that HW should be equal to 47 meters. And we also know the radius of the well RW equals 0.1 meter. And when the R0 equals 200 meters, we can determine that the Q should be equal to Q sub 200 discharge to be equal to the 0.12 cubic meters per second. And when R sub 0 equals 250 meters, we can determine that the discharge should be equal to 0.117 cubic meters per second. Sorry. And when R0 equals 300 meters, we can determine that the discharge should be equal to 0.114 cubic meter per second. And now we need to determine the percent error. So the first percent error should be equal to the observed value 0.12 minus the expected value 0.117 divided by 0.117, the expected value. So this value is positive 2.6%, and the other percent error should be equal to the 0.114 minus 0.117 divided by the 0.117. So the value is negative 2.6%. So we can get a conclusion that about plus or minus 2.6% change in discharge for plus or minus 20% range of R0. So we finish this problem. For the last problem, a 40 centimeter diameter well draws water from a 13.5 meter deep unconfined aquifer at a rate of 0.0151 cubic meters per second, and the drawdown at the observation well 15 meters away is 1.5 meters, and the drawdown at the well is 6.5 meters. And we need to determine the radius of influence of the well, also determine the drawdown at a distance of 100 meters from the well. So we know the K value is not given in this problem, so we can use equation 7.16 with the observation well and the pumped well data to obtain it. So from the equation 7.16 in the textbook, we know h squared equals HOV squared minus the Q divided by the pi times K times the natural log of RB divided by the R. And from the problem, we know the drawdown at the well S is 6.5 meters, and the depth of the unconfined aquifer H0 is 13.5 meters. So we can determine that H equals HW equals 35.5 minus 6.5, so equals 24 meters. And we also know the drawdown at the observation well is 1.5 meters, and we know H0 equals 30.5 meters. So we can determine the HOB should be equal to 30.5 minus 1.5, so HOB should be equal to the 29 meters. And we know the Q equals 0.0151 cubic meters per second, and we know the RB should be equal to the 50 meters, and R should be equal to the 0.5 meter. So we can determine that the K value should be equal to the 0.0001 meter per second. And then now we can use equation 7.15 to find the radius of influence. So from equation 7.50, we know HW squared equals H0 squared minus the Q divided by the pi times K times the natural log of 0 divided by RW. And we know HW equals 24 meters we determined before, and H0 is the depth of the unconfined aquifer is 30.5 meters, and K equals 0.0001 meter per second, and the Q equals 0.0151 cubic meters per second, and RW equals 0.2 meters. So we can determine that the radius of influence R0 equals 318 meters. And then we still use the equation 7.16 to determine the drawdown at a distance of 100 meters from the well. So we know H squared equals HOB squared minus the Q divided by the pi times K times the natural log of RB divided by R. And we know the H equals 24 meters and the Q equals 0.0151 cubic meters per second, and the K equals 0.0001 meters per second. And now the ROB should be equal to the 100 meters, and the R equals 0.2 meters. So now we can determine that HOB should be equal to the 29.6 meters. So now we can determine the draw down should be equal to the 30.5 meter, the depth of the unconfined aquifer, minus the head at the observation well, so 29.6 meter. So we can determine the drawdown should be equal to the 0.9 meters. So we finished this problem.